Imagine sitting inside one of the fastest trains in Europe. The ride is smooth, people are reading, talking, drinking coffee. Then, a violent metallic bang comes from beneath the first passenger car. A long strip of steel punches through the floor between the seats. Nobody knows what it is. Nobody can see what is happening beneath the train. And the train does not stop. It continues toward Hamburg at almost 200 kilometers per hour, with the steel still trapped underneath it. A passenger finds the conductor 2 cars away and tells him that something serious has happened. The conductor starts walking back to inspect it. He never reaches the damaged carriage. Minutes later, the hanging metal catches a railway switch outside a small German town. Then the train reaches a second switch. Carriages leave the rails. One swings into a concrete bridge. The bridge collapses onto the train. 101 people are killed. And all because of a piece of steel that nobody recognized until it was too late. So, what was it? And how could a train keep moving after such a violent failure? This is the failure chain of Eschede. June 3rd, 1998, ICE 884 named Wilhelm Conrad Röntgen is traveling from Munich to Hamburg. Nearly 300 passengers are on board. At the time, Germany's Intercity Express represents the future of railway travel. Fast, quiet, engineered for safety at very high speed. At 10:56 in the morning, about 6 kilometers before Eschede, something beneath the first passenger car breaks. Passengers hear the impact. Then they see the steel strip standing through the floor. One end is inside the carriage, the other is still beneath the train, striking the track as the ice continues north. There is no automatic alarm telling the driver that what happened. From the front, the train is still moving normally enough to continue. Inside the damaged carriage, a passenger goes looking for a member of staff. The conductor immediately follows him back. Railway rules require him to inspect the problem before using the emergency brake, because an unnecessary emergency stop at high speed can create its own danger. So a later court expert concluded that the conductor could not have prevented the crash after receiving the warning. There simply was not enough time. So at 10:59, the damaged train reaches the first switch south of Eschede station. The steel hanging underneath catches part of the track and tears it upward. Heavy components strike the underside of the carriage and lift wheels away from the rail. Then those derailed wheels hit the second switch and force it into a different position. The front wheels of the third car continue straight. The rear wheels are sent toward a side track. For a fraction of a second, one carriage is being pulled in 2 directions at once. At almost 200 kilometers per hour, it swings sideways. Directly beside the railway stands a concrete road bridge. The carriage strikes one of its supports. The bridge collapses. The leading power car and the first 2 passenger cars have already passed beneath it, but the following carriages meet falling concrete. They crash into the bridge and into each other. Cars fold, climb and compact into a wreck only a few meters long. The front power car continues for almost 2 kilometers before stopping. The driver learns by radio that he has passed the signal box alone. The rest of the train is gone. Investigators now follow the destructions backward, from the bridge, through the second switch, through the first, and back to the strange strip of steel. It was not part of the track. It had been traveling with the train, and before it became a straight strip, it had been circular. It was the outer tire of a wheel. This wheel was not made from one solid piece of steel. To reduce vibrations and make the ice more comfortable, engineers had placed rubber elements between the center of the wheel and a separate steel tire around its outside. The design gave passengers a smoother ride, but under the weight of the train, the outer tire flexed slightly with every rotation. The wheel that failed at Eschede had traveled almost 1.9 million kilometers. As its tire became thinner through normal wear, a fatigue crack began growing on the inner side where it was difficult to see once assembled. So every journey pushed it farther through the steel. Until at high speed on June 3rd, the final section broke. The circular tire opened. It peeled away from the wheel and straightened into the steel band that pushed through the floor. But the center of the wheel remained on the rail. The wheel had failed. The train could still move. That is what allowed it to reach the switches, and investigators found one more disturbing detail. According to the railway's maintenance rules, the wheel was worn, but it was not yet worn out. The broken wheel measured about 862 millimeters across. The official replacement limit was 854. It was still legal to use, but later engineering analysis concluded that for the real loads of high-speed service, the limit should have been closer to 880 millimeters. The wheel was officially acceptable while already operating beyond what later analysis considered safe. So this was not simply one crack missed during one inspection. It was a design that accumulated fatigue, a maintenance limit that did not reflect the real forces, a failure that left the train moving, and two switches positioned immediately before an exposed bridge support. After Eschede, the ice fleet returned to solid monoblock wheels. Inspections were strengthened and protection around bridges on high-speed lines was reconsidered. But those changes came after 101 people had died. The visible disaster lasted only seconds. The real accident had been building for years. One journey at a time, one rotation of the wheel at a time. If you found this story interesting, subscribe to Failure Atlas for more stories about small, hidden failures that grow into something much bigger. And tell me in the comments, which link in this chain should have stopped the train first? Thank you for watching and see you in the next video.